the first topic I'm going to talk about is making decisions. So that's what a computer usually does. It makes decisions to solve problems. Um, but the fact that they can solve problems is a complex consequence of its capability of making decisions, because you make decisions, then you go through a path. Here is that a computer evaluates this question. For example, you are looking for a creature, but but you want to choose one of these creatures. In this example, you have from a piranha to coal, and in order to choose one of them, you have to ask many or less questions in order to find your target. So you make a first answer. You try to guess smaller. Is it smaller than a bicycle? If it isn't, well, goes on the call. And you have just two questions to get here. Um, on the other side, if your animal were smaller than a bicycle, you would have found much more animals that fit in this category. So you can look at these options from a piranha, house cat, a robin, a salmon, mouse, and a virus. Um, because here you have more animals, so you have to ask more questions to know about this specific creature you're looking for. For example, here you have one, two, three questions to get these two animals. You have to five questions to know if your creature is a virus or it is a mouse, because they are very similar. In if we take this set of questions as the main criteria, you have to do five questions. Here you have to do three questions. Um, this quantity of questions, this number of questions, five or two or three. You are doing questions, and they are computer. Computer. This question goes to its memory. This information, this is recorded in the memory of this PC. So so here we find the concept of information that is obtained by making questions. So making decisions. So there's a direct relationship between questions, decisions, and information. The more questions you do, the more information you have. And well, let's gotta let's gotta erase this. It's gone. So this system is imperfect. Why do I say that? Because this system allows system makes one, two, three, four, five questions to find an answer, and that's not very convenient because, for example, you have four options here, you know, so you could separate this for see, I'm sorry, you have eight options here. You can separate this into groups with a question. So you go one question. Note that we made five questions before. Um, but now you have done one question. Then you ask another question, and you to separate this. Suppose that the first question located you here. So the second question locates you here. And the third question leaves you with an answer. Same thing for the other side. First question, then you make the second question. You get this two or this two. Then you make the third question. And you get this one or this one. And you just have done three questions. And you have chosen every element of the list. That's efficiency. That's an important concept of information theory. It has been used to create some models that needs the smaller quantity of questions to get a precise quantity of information. So it's not just ask as a, as a segment. You just have to be smart asking. An intelligent asker. Yeah, you can use this to make this face recognizer, because you can ask questions about the hair, the glasses, the emotions, the mouth, etc. You can ask every question you want to ask, distinguish one face from another. For example, here we are talking about one question that divides four objects into groups of two objects. The first question could do this, and the second question could do this. But you have to be smart to make the correct questions, because maybe you would choose a question. Well, you have two questions. The first one is open mouth. Yes, they have open mouth, and they don't. But if you ask about open eyes, well, here you have the answer if it's the second question. But here you don't have the answer. So it's a bad question. If she was blind, let's suppose she's blind, and you make the second question, who are with the eyes open? Well, it would be a correct election, because you can find her and her, and they both choose a specific subject. So that's fine. It's important to know this, because you spend some resources when you ask questions. So that's the ideal scheme, because you make a question and divide in groups of two. Make another question and you're still creating groups. You make another question and you find an answer. In every case you are asking. You are not leaving one element free alone, because you are wasting your information if you just exclude one element. You must be smart to separate your answers. Also, well, this is really bad. This is not effective, because here you're asking and you're creating two groups, but in this group is left alone, so you're not classifying very effectively, because you just excluded one element from the group, and that's not really convenient, because more information about him, and the information that you get here with all of these fellas is not so specific. Maybe it's not relevant, but that's not an absolute statement. So we must be careful when we talk about this. But when we talk about this is good one guy, I am serious. This is we can be losing content about him, or maybe we ask some question here and we have forgotten him, but this applies to him. So it's important to be organized when you make groups, so you don't make bias. Well, um, here another scheme. Ah, then and here we introduce the concept of order because the questions have an order. The order, different order they are executed, the more different outcomes you will have. And here, um, well, we see a failure of classification. These phases are almost as different as they can be. So one reason that the decision tree failed so badly was that the first few questions focused on hair color, and the decision tree contained no faces with long hair. The lack of long hair faces in the decision tree made it easier to badly misclassify a blonde hair face. And here we want we look beyond the problem of yes no questions. So, for example, how would you use a decision tree to sort a deck of cards? Well, that implies a more group of complex logical gates. We are not covering that yet, so we're gonna see that in the future. And now that we have gone through this quiz, now we're moving to making decision. Uh, what I'm talking about, I just finished making decision part, so we are gonna search for solutions. So we talked about decision trees, algorithms, instructions, um, efficiency of information, the making of questions, the smart way to create your questions, the order of your questions, and now you're going to apply this to the pursuit of a solution. And well, I think we have. I got it. I got it. I got it. I am waiting for this scheme. Well, we got it. So here we have a city which is divided by you could say two rivers. Maybe two rivers, and these rivers are connect different parts of the city by these bridges. 4, 5, 6, 7. And well, you you may have heard about these experiments with the travesty of a rat through a maze, and the rat reacts to the walls of the maze. So when the rat goes into the maze, it detects the wall and it changes its direction. And finally, it goes out of the maze because it has learned to decide. So Well, here we are going to do something similar. We're going to try to go through these bridges. For example, one experiment, the first experiment we're going to try is going through the 7 bridges just one time, no more than that. So we tried. We're 4, we're 5, we're 6, and well, we can't go get out. So we blew it. Maybe we're gonna try another path. 1, 2, 3, 4, 5, 6. No. 1, 2, 3. No. 1, 2, 3, 4, 5. No. So it's impossible. Not the fact that I have tried 3 times is not enough to say that it's not possible to travel around the 7 bridges without repeating one. But you can calculate this with a simple permutation. That's the answer. You could have tried this number of times because you can choose. Well, I'm going to explain this number. You can choose seven options. Well, you can choose this, you can choose this, you can choose this, etc., etc., etc. Then, when you have, for example, chosen this, you at first had 7 options. Now you have 6. Then you will have 5, 5, 5. Then you will have 4, then 3, then 2, and 1. So you multiply all of them, and you have the total number of proofs you would have to do if you want to prove that 7 factorial number of proofs would need to be made to discard the possibility that one can go through this path without repeating bridge. But as hard as you could try, there's no answer because it just doesn't work that way. You will have to repeat a bridge in order to cover all the 7 bridges. And well, we can be more practical. Well, here the computer gets stuck. It tries to solve the problem. Then then the program makes some smart questions. For example, it says, I'm sorry. It says, what is the fewer number of bridges you can cross before getting stuck? And the answer is 1. No, because you can still go through. You can find a path. 1, 2, 3, 4 options. 2, no, because you always will have a second option. 3, maybe yes. I'm gonna prove this fast. 1, 2, 3. So we don't have where to go. We don't have options. We get stuck here. We get stuck here, and we don't have options. So 3 is the fewest number of bridges you can cross before getting stuck. You can talk about the fewest number, the highest number, which is 6, and so on. You are extracting that. about it. Then you have, we will try to find one by moving around randomly. That's what we talk about. Finally, we could prove that multiplying 7 per 6 per 5 per 4 per 3 per 2 per 1. And it's not very practical for us, but computers do it very fast. Let's see when it's a simple adjustment question, but set of questions. But when it goes more complex, you will have more problems. And we're gonna look at that in the next episode, which is about thinking with graphs. And here, as we explore the possibility of a brute force solution, um, and knowing that it's only works good for the small decisions, you have to know that it's possible to make progress and figure out how to solve the problem for cities with many more reaches, a real number, by thinking about the problem in a more general way. So, what does it mean? We're gonna see that in the next class.